This lesson is about light as it goes through a lens and how that light bends as it goes through the lens. You'll notice in many of these slides I've already written on them. That's because this particular set of notes is very difficult to write on this program, so I'll highlight the things that I've drawn as I'm going through. Imagine that I have some light rays. We'll say that they're coming here and they're going parallel to one another and through this piece of material, and this piece of material, the triangle, the square, and the other triangle, all of those are going to be a medium which light is slower in than it is outside. So what we do is we see that light is going to bend towards the normal, and then it's going to bend again away from the normal as it exits the slow material. And this middle square, the light will go straight through, and then this triangle on the bottom, the light will bend towards the normal, and then as it goes through into the fast medium, it'll bend again away from the normal. So this particular arrangement of material ends up bending light so that it's all coming together. It's converging, light is coming together. And then if I look at the next picture on the right, as that light goes through, it's going to bend towards the normal and then bend away from the normal. It'll go straight through. Light will bend towards the normal and then it'll bend away from the normal. So you can see that that light is all spreading out after it goes through the lens. In other words, it's diverging. So we get what's known as a converging lens and a diverging lens. A converging lens is a lens that is thicker in the middle, which then causes light to come together to a point. A diverging lens is one that is thinner in the middle, which causes light to spread out. The light that's spread out, though, appears as if it came from a single point. There are lots of vocabulary words that you're going to need to know in order to understand and be able to explain images that are formed when light goes through lenses. The first thing I want to highlight is something known as the principal axis. So this is our lens. We have a lens right there. And if I were to draw a line perpendicular to that lens, that's called our principal axis. And then a line that goes straight through the lens vertically, that's called our lens axis. The point at which the lens axis and the principal axis meet, that's known as our vertex. So I have that right there. We'll be taking a lot of measurements from the vertex. We also have something called a focal point. So we have a focal point on the right-hand side and on the left-hand side. The focal points are going to be points at which parallel light rays meet, which I'll explain later. And then the distance from the vertex to the focal point is known as the focal length. We also have 2f, which is just double the focal length, or twice the focal point's length. Another thing that I want to highlight is that when light enters a lens, it will bend twice. It will first bend when it hits the light, or the glass itself, or excuse me, the lens. It'll bend there, and then it'll bend again when it exits. But for convenience sakes, we will just simply draw the bend occurring one time, and we'll draw it occurring at the lens axis. Again, this is just to make the drawing more convenient. It is certainly not how light actually bends. So it turns out with converging lenses, if you have the object a particular distance away from a converging lens, we can get very different results as far as what we're going to see from that lens, the image. If the object is very close to the lens, then we're going to see something very different than if the object is quite far from the lens. As a matter of fact, there's 6 different locations for where an object can be relative to a lens that can give us 6 different images. Those 6 different locations are location number 1, which we see is far left. I have a sun drawn here. What that is supposed to illustrate is when you have light rays that reach the lens and they are parallel to one another. And so the sun being so far, the rays from the sun that actually make it all the way to the lens are essentially parallel to one another. This also could work if you were to take a laser pointer and shine it parallel with the principal axis. The same idea would happen. But anyway, so when you have an object really, 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 really far away, we call that case number 1. Case number 2 is when we have an object that's giving off light that's far away. It's not infinitely far away, but it's far enough away that it's more than 2f away. Case number 3 is when you put your object exactly at a distance of 2f away. Case number 4, when you put your object in between f and 2f. Case number 5 is if you put your object exactly at f. And case number 6 is if you put your object in between f and the lens itself. So all 6 of those object locations will give different and unique image descriptions and locations. Diverging lenses are not quite as interesting in that sense. If you have an object infinitely far away and thus parallel rays, you'll get a particular image, and that's going to be case number 1 for diverging lenses. And it turns out if you put an object anywhere else other than infinitely far away, you're going to get the same generic image. So we really only need to look at one other case, so which we call case number 2. So let's start off with case number 1 in a converging lens. If I have light rays from an object that are coming to a lens parallel to one another, which is what I've drawn on this picture. These light rays are headed towards a lens from some object that's causing them to be parallel to one another. Again, something really, really far away can make this happen, or just simply a laser pointer. By definition, a converging lens will take and bend light, parallel light rays, to the principal axis, will bend them so that they cross right at the focal point. So we end up getting is all of the light sort of smashed together to this one point. And so what we see is this image that we see is just going to be a blob of light. You're not going to really be able to distinguish what it is you're seeing. It's point-sized. It is located at the focal point. It is on the opposite side of the lens from the object, because remember the object was somewhere over on the left side, and now the image is on the right side of the lens. So they are opposite to one another as far as sides go. And then this last piece, it says we are having a real image. What that means is there's actually light that is coming together, and when the light comes together, it interferes and we get a brighter spot. So that's real light. You can actually capture it on a card, but you can see it very clearly. If you've ever tried to burn ants with a magnifying glass, this is what you're doing. You're basically taking the sun's rays, the sun's light, and having it go through the magnifying glass, and you're finding that distance away where you can concentrate the light to one point, so it's very intense, and so that gets very hot, which then people have burned ants for. I've never done it before. So this table is going to be very useful as you're trying to go through and describe the image itself. How it's set up is the top part of the table is all about the converging lenses, and the bottom part is the diverging lenses, and you see the cases that are marked. All of the cases are relative to where the object is. So the thing that's giving off the light, where is that? If the thing that's giving off the light is infinitely far away, that's case 1. If the thing that's giving off the light is farther than 2f, that's case 2. If the thing that's giving off the light is at 2f, that's case number 3, etc. And then you can see that the table splits, and then we have diverging lenses at the bottom. You are going to fill this table out, and you're going to be able to then reference at any point what the image is like based on where the object is. So we'll build this table together. So I quickly referenced what a real image was. And again, a real image is when there's light rays that actually converge and make an image. The left 2 pictures here are real images. So I'll start with this bottom one. There's light coming in from behind this person, and you can see it from the sun and the window, and then he's actually able to give us an image of what was behind him. So behind him there's a person and a door, what it looks like a door and a person, and you can see that now there's a door and a person, an image of it. It's much smaller than the actual door and person. And you'll also notice that it's upside down. If I look at the picture above, it's not shown, but there's a candle over here. And then that light goes through the lens and actually gives me an image of an upside down candle, and that's real light. So that's a real image. Notice with both real images, they are upside down. So that's something that all real images have in common when we talk about lenses. Now, virtual images look as if they're trapped in the glass. So you can see that right here, this is a virtual image of the meter stick. It's certainly not that small. It looks trapped in that glass. This is a virtual image of this woman's eyeball. Her eyeball is not that large, but what we're seeing is an image of her eyeball, and that's a virtual image. What you'll notice with virtual images is that they are right side up. In all of these drawings that we're about to do, you are going to draw 3 convenient rays. And it is required that you draw at least these 3 convenient rays. Understand that when I look at a candle, there are so many light rays coming off that candle. There's light rays going, from the top of the candle up and to the right, up and to the left, straight up, heading down, etc. There's light coming off the middle of the candle in all directions. There's light coming off the bottom of the candle in all directions. So there's millions of light rays. We're going to choose 3 that we know exactly how they behave and which way they're going to bend. So the 3 convenient light rays are what we're going to use. You must draw all 3, even if it's difficult. I know that you can certainly locate an object using 2 rays, but we're going to require you to do 3. And so we've landed on the 3 convenient rays we're going to draw for converging lenses. First one is going to be when I have a parallel light ray. So imagine that a light ray is parallel to the principal axis. That's going to bend so that it goes through the opposite side F, just like case number 1. Parallel light rays went to the focal point. The second convenient ray that we're going to draw is a ray that's headed towards the vertex. It's going to keep going in exactly the same line that it's headed in before, so it just goes straight. And then the third convenient ray is a ray that goes through the same side F, so the focal point on the same side of as the object. That one, once it hits the lens, it's going to end up going parallel. And where those 3 rays meet, that's where you can find the image. So let's take a look at case number 2. So case number 2 is when you have your object beyond 2F. So on the left-hand side, you can see that my arrow is my object. We see F and we see 2F, and so my object is beyond 2F. Now I've defined a few vocabulary type things that we're going to use in equations later. One, DO is the distance to the object, and it's the distance from the lens axis to where the object is, or you can think of it from the vertex to where the object is. That's DO, distance to the object. DI is going to be the distance to the image. So the image is going to be found right here. And I'll explain how you get that in a moment. But the DI is going to stand for the distance from that lens axis or the focal point, or the vertex to the image. And then we've got HO, height of the object, so how tall is the object? And then HI, height of the image, how tall is the image? So let's start by looking at those 3 convenient rays. So we'll start with parallel. As I'm thinking this through, I probably should explain to you that we understand that if light is going to go through, light's going to come off the bottom of this arrow, let's say, and it's going to go in all directions. But one of the directions it's going to go is directly towards the lens. And so as it hits the lens, we know it's actually not going to bend, and it's going to go straight through. So we can say with certainty that the bottom of our object is going to be somewhere on the principal axis. So what we're going to do then is we're going to locate where is the top of the image found. And then we can actually draw where the image is. So what I'm doing now is I'm going to draw the 3 convenient rays for the top of the object and see where they cross so I can locate the top of the image. Okay, so first one was a parallel light ray. So this ray here is parallel to the principal axis, and we learned that that is going to bend and go through the focal point. So that's what I've got so far. The second convenient ray says if you take a ray, so again I'm going from the top of the object and I'm headed towards the vertex, that ray is just going to keep going straight. So you can see right now 2 of those rays have already crossed. But let's for good measure do the third convenient ray. The third convenient ray says if you were to draw a ray from the top of the object and go through F on the same side, then that one is going to hit and it's going to go parallel to the principal axis. So I can see all three of these rays have crossed right here, which means that the top of the image is right here. And we know that the bottom of the image was somewhere on the principal axis, so then we get that this is our image. So we have to describe the image. Well, at the top I have image description. Where is it? Well, it's between F and 2F. Here's F, here's 2F. My image is somewhere in between those two. It is inverted, it's upside down, and it's real. Those light rays did cross. It is smaller than the object is. So if you look at the object, it's about 2 boxes high. And if you look at the image, it's just a little more than 1 box. So it's smaller. It is on the opposite side of the lens from the object. Again, the object was on the left side. The image is on the right side of the lens, so that's opposite side. Now, this is going to be confusing at first, but we are going to try and determine what the signs are going to be with some of these variables. DI can be positive or negative, and it turns out that if your image is on the opposite side of the lens from the object, you're always going to have a positive DI value. So distance to the image is going to be considered positive. And then the last thing I have here is magnification and height of the image. Well, since it's upside down, we are going to describe the height of the image as being negative, and we're going to describe the magnification as being negative. If it was right side up, then we would describe the height of the image to be positive and the magnification to be positive. So for each of the remaining cases, what I would recommend that you do is that you try them on your own and then come watch the video. So case number 3. Case number 3 is when you have an object placed exactly at 2F from the lens. The first convenient ray, the parallel ray, when it hits the lens axis, is going to bend and go through the focal point F. The second convenient ray is going to go through the vertex and continue through straight. And the third convenient ray is going to go through F on the same side, and then it's going to bend to go parallel to the principal axis. Where those 3 rays meet is where we find our image. So this is our image. Let's describe the object, or let's describe the image compared to the object. 1, we can see that the image is at 2F. It is the same size. HO and HI are the same magnitude. It's about 2 boxes and 2 boxes. It is on the opposite side of the lens from the object, so DI is going to be a positive number. It is real. It is upside down. And we know that all real objects are going to be upside down with lenses, and so our magnification and height are both going to be turning out to be negative numbers. Case number 4. If I were to have an object that falls between F and 2F, here are my 3 convenient rays. My parallel ray is going to bend through F. My ray through the vertex is just going to keep going straight. And my ray that goes through F on the same side is going to go parallel to the principal axis. So where those 3 lines cross, that's where we find our image. So there's our image. If we were to describe the image compared to the object, it is located beyond 2F. It is on the opposite side from the object, so DI is positive. Again, it is real light converging, so it's inverted. Magnification and height are both negative. And as far as the size, the object is, less than a box tall, and the image is more than 1 tall, so that's going to be larger. This next one is our trickiest one. If I were to try to draw the 3 convenient rays, I will only be able to draw 2 of the rays in this case. The case is when you have the object located exactly at F. So our parallel light ray is going to bend and go through F. Our ray through V is going to keep going straight. But the thing is, those 2 lines are just never going to cross. And so there is no image ever. So if you were to take an object and put it exactly at F distance from a lens, you can try and try and try, but you're never going to see that object clearly through that lens. It's no image. And then we get case number 6, which is also quite tricky. Case number 6 is where you have the object actually in front of F, or in other words, the object is between F and the lens itself. So let's draw our convenient rays. I know there's a lot of drawing going on this slide, but try and follow along with what I'm doing right now. The parallel light ray is going to bend and go through F like it's been doing the whole time. The ray through V is going to continue through V. But the last one is very tricky. A ray through the F on the same side. So this green ray that I've drawn, it is at the top of the object, and it's going to the lens, and it would go through F. It's in the same line that F is in. See that? So it's in the same line that F is in, but it's behind it, which we've never had before. The F has always been in front. So it's behind. So you end up having this line that's a little bit trickier. It goes through F, and it also goes through the lens, starting from the top of the object. And we know that when you have a ray that is angled so that it's through F, that one is going to go parallel. So what I have here is I have these rays, and they're all moving away from one another. They're spreading out. So are they ever going to cross? No, they're not. So there's not going to be a real image formed. However, if you are an observer and you were to be on this side of the lens, then you're receiving light that's spreading out. It looks like it came from a singular point. So your brain and eyes together interpret as if, the green light ray, we interpret as if that green light ray came from back here. And we interpret that blue light ray came from back here. And we interpret that the red light ray came from back here. And so it seems as if the light rays originated from here. And so we perceive that image, like when we look in the mirror, same kind of thing. We perceive the image to be located on the same side, actually, of the lens as the object. So it's on the same side, which means now we're going to get a DI value that's negative. It's located not necessarily beyond 2F, but it is located behind the object. For the first time, we've had a virtual image. No light, real light is actually crossing. It's where we're perceiving the light from, and it is upright. And so since it's upright, magnification and HI are both positive. And then the other thing is the image is always going to be larger than the object is. Diverging lenses are very similar in how they work to converging lenses. There's a few key things that we have to change in order to make everything work out. The first thing is F and 2F are going to be negative for diverging lenses. So if I tell you that you have a diverging lens and you go to use an equation, you're going to need to plug in F as negative. Or if I ever tell you that you have a lens of negative focal length, right away that should let you know that you have a diverging lens. Now the convenient rays for a diverging lens is, again, they're similar. It's a parallel light ray like we had before, but instead of bending and going through F, it bends away, essentially, as if it came from the same side F. This one is the same as it was before. Ray through V keeps going straight. Awesome. And then a ray in line with the opposite side F bends to go parallel. So we'll model this in case number 2. So case number 1, we only have parallel light rays because remember, case number 1 is when an object is infinitely far away, and so the light rays that are reaching our lens are essentially parallel to one another. So I have a parallel light ray, a parallel light ray, a parallel light ray. Parallel light rays, by definition for diverging lenses, they bend as if they came from F. So this is the direction that these rays are headed. But again, they bend as if they came from F, which here is our F. And then we can say a ray through V keeps going straight. Would be another way to look at this one. And so these 3 rays that are on the right-hand side, these 3 rays are never going to cross. And so again, and as an observer, if I was on this side, I could say, well, those rays came from F. And so there would be a virtual image, and it would be located at F, which we're using as a negative number. So we've got the image located right here. It's located at negative f. It is virtual. It's technically upright because it's virtual, but it's point-sized, so to talk about it being upright is somewhat silly. And then it is on the same side of the lens as the object, because remember our object was somewhere here. I'm getting parallel light rays essentially. And so the image is also on the same side. It's on the left side of the lens. So DI is negative. Last case for us to draw is case number 2. Case number 2 is when you have your object anywhere other than infinity. So I just happen to draw my object between f and 2f, which really doesn't matter, but that's how I decided to go with it. So let's try these 3 convenient rays. The parallel light ray is going to bend as if it came from f. So that's the direction that it's heading. The ray through V keeps going straight. That was just like converging lenses. Then this last one it's tricky. A ray headed for the opposite side F. That one bends to go parallel. And you can think of it as if the light was going the other direction. If you thought about the light coming instead of from the left, if you think of it as coming from the right, this would be a parallel light ray, and it would bend as if it came from F. Right? So this is our F. It would bend as if it came from F. So one that's headed towards the opposite side F would bend to go parallel. So once again, where do these light rays meet? Well, they don't. So we're going to have a virtual image and not a real image. So let's figure out where this virtual image is. So we interpret, this blue light ray that's coming towards us, we interpret it as if it came straight back from this direction. And the green light ray came back from this direction. And the red one came back from this direction. So where those rays, those perceived rays meet is where we find our image, our virtual image. And so you can see that it's, since the object is here and the image is here, the image is in front of the object, and not necessarily in front of F, but in front of the object. Again, it's on the same side of the lens as the object, so DI is going to be negative. It is smaller than the object. It is virtual and it is upright, so magnification and height will be positive numbers. So what I've done now is I have filled out this table to reflect all of the information that we put in the notes. And what's going to be really great about this is I'll ask you questions like, suppose a lens has a focal length of 10 centimeters and an object is placed 15 centimeters from the lens. Describe the image. So I'm thinking, okay, if the focal length is 10, then 2f is 20. And it said the object is 15 away. So that tells me the object is between f and 2f. So I'm looking, okay, if the object is between f and 2f, that's case number 4. And I already drew that out. I know that the image is going to be beyond 2f. I know that the image is going to be larger than the object. I know that the image is going to be on the opposite side. I know that the image is going to be real, and I know it's going to be inverted. I know that DI is going to have a positive sign because the image is on the opposite side of the lens. I know that since it's a real image, it's going to be inverted, and so height and magnification are going to be negative. So if I can just figure out where F is to F and where the object is located, I should very easily be able to trace what's going on with the image. So finally, we get to start looking at how we're going to solve mathematically these problems. And we have something known as the thin lens equation. And the thin lens equation is right in the upper left-hand corner. It is 1 over f, or 1 over the focal length, equals 1 over di, 1 over the distance to the image from the vertex, plus 1 over do, which is the distance to the object from the vertex. The only units requirement is that all of the units are the same. So they can all be centimeters, they can all be meters, they can all be kilometers. They just need to all be the same. And then you can rearrange this equation to get do by itself, di by itself, whatever you need to do. The second equation that we have comes from the idea that there's some similar triangles, and if you want to see the similar triangles picture, you can see it on the upper right-hand corner. But due to similar triangles, we end up getting that magnification is going to be the height of the image divided by the height of the object. Or it's also going to be negative di over DO, which is, again, because of similar triangles. And magnification, the idea of HI over HO should make sense. If the image is twice as big as the object, magnification is 2. Now, the thing with magnification is, remember, if the image is upright, magnification is going to be positive. And if the image is inverted, magnification is going to be negative. If the magnification is between 0 and 1, and let's not worry about the negative or positive. Let's just say if the absolute value is more than 0, less than 1, then your image is going to be smaller than your object. If your magnification is greater than 1, again, the absolute value of magnification, if it's greater than 1, then that means the image is bigger than the object. So again, the positive and negative sign for magnification simply just mean whether it's upside down or right side up. And then if the number is greater than 1 or less than 1, then that's going to help you determine whether it's bigger or smaller. So, game plan. What you're going to have to do is one of 3 things with these lenses. You're going to have to either, 1, draw a ray diagram and locate an image like we did on the previous slides. 2, given a focal length and an object location, describe the image. So using that big table, can you describe the image, what it's going to be like? Or you could also, draw it and find out for yourself what it's going to be like. Or 3, you're going to mathematically describe the image. And so that's what I'm going to do right here. I have an example problem. It says, where is the image of an object that lies 7 centimeters from a lens with a focal length of 5 centimeters? So as I'm pulling information, it says, where is the image? So that's going to be DI. And the object that lies 7 centimeters from the lens, that's going to be DO. And then the focal length is going to be F. So that's going to be our F. So as a reminder, our equation was 1 over F equals 1 over DI plus 1 over DO. So I'm going to plug some numbers in. I've got 1 over 5 centimeters, because remember 5 centimeters was the focal length, equals 1 over DI, which DI is what I'm trying to figure out. Where is the image? Plus 1 over DO, and it says the object was 7 centimeters from the lens. So if I rearrange the equation to get DI by itself, I get that DI equals, and I get a positive number, 17.5 centimeters. Next it says, what is the magnification? So magnification can be HI over HO, but I don't know that information. It can also be negative DI over DO. So I take negative 17.5 centimeters, which is what I got earlier, divided by where the object is located, which was 7 centimeters, and I get negative 2.5. There are no units for magnification. As far as the negative is concerned, the negative is simply telling us that the object, or the image, is upside down, and the 2.5 being greater than 1 means that the image is bigger than the object. So now let's talk about what case this is. So if I have F is 5 and 2F is 10, then the object is 7. That means it's between F and 2F, which gives me case number 4. And so if I go back and look at the table, case number 4, I should have an inverted image, which makes sense because I got a negative number here. It should be larger, which makes sense because I got 2.5. It should have a positive DI, which I had. The image location should be beyond 2F, which it is because 2F is 10 and this is 17.5. And so all of those things should help kind of confirm your findings.